Hi, everyone. Welcome to the Climate Confident Podcast. My name is Tom Raftery. With me on the show today, I have my special guest, Jan. Jan, welcome to the podcast. Would you like to introduce yourself?
Thank you very much, Tom. I'm happy to be with you today. Yes, I'm a Norwegian living in Sweden, with background as an officer and economics degree as well. And then I've been flying aircraft actually for 25 years, and last 22 in SAS, also air show displays with bomber aircraft, etc. And while I was flying, I made a large property deal, you may say, which gave me some liberty for some time at least. And then I had to decide what do I now do for the next 15 years? Just keep on flying, which was comfortable, nice, and fun in many ways with nice colleagues, or do something more meaningful. Well, in my drawer, I've had many patents ideas over the years and seen time and time again other people taking, let's say, my ideas to the market 25 years later. Slightly irritating, but I had one left there, or that is the better ones. That was a wave power solution. I drew it when I was 25 years old. That's quite some years ago. And I was thinking that, well, now I had a climate crisis going into an emergency and nice to do something meaningful. So after 1 year waiting for that back, I quit SAS and basically said, now I'm going to save the climate crisis and live part of it with profitable wave power.
Nice, nice, nice. And before we go any further on that, I should just mention for people who are watching this, if you're seeing my face looking a little weird, it's not that I got into a bar fight last night. No, I had a minor surgery earlier this week. And so hence the bandage and the bruising. And so that out of the way, sorry, Jan, we'll come back to your wave power idea. So tell me a little bit more about it, because wave power has been around for a while, but hasn't really taken off. There are multiple challenges with wave power, not least the fact that it's expensive, and also the fact that the marine environment is notoriously unforgiving. So how is your wave power solution different, or is it? How are you addressing those kind of challenges?
Let's say, start with the last question first, how it is different. Basically, the lifting force is 4 times higher than the second best, multiple times more than most other ones. The output is, well, officially it's 500 kilowatt now on the web page, but tests have shown it's coming at least to 700 kilowatt, which also is multiple times more than other ones. And then when you compare the weight to power ratio, we are exceptional. Then add to that the number of parts, etc., complexity, we are quite different. That was enough for the bragging, but then it comes into, there are two ways of extracting energy from wave power. The waves, they have a circular motion in the water, seen from the side, and they also go up and down, as we all know. And you can extract by having something like a plate in the water, horizontal or vertical, and then getting power from, let's say, reducing the speed of those particles, the weight of the particles by Newton's law. Or you can lock air in the water. So when the wave is rising, you have a buoy of some sort standing still, then you lock energy in the water. And once they go upwards, then you have it coming upwards, and you have a mechanism that converts that lifting force into energy. And there are many solutions on both parts. Interesting enough, we have done quite heavy, let's say, simulations looking into both aspects just to compare them. What we have found is that if you are going by the particles, Newton's law, you need 30 times the area in the water to equal the amount of power or size of the unit needed when you use Archimedes. And 60% of the solutions are on the Newton side. So in our opinion, that is very, very difficult because material has weight, cost money, and transportation, deployment, everything is difficult when it's big and produces little power. So we have to go by Archimedes. And then most units are round buoys, And the limit in size is normally from 8 to 12 meters due to the wavelength being, in the summer seasons at least, down to 30 meters. If it is too large, you're cutting the waves. So if you have around one, you can lift at most perhaps 150 tons of this size, put down in the water. Our case, it is rectangular because the waves are also mainly rectangular, at least the larger swells coming in, the ones that are created across the Atlantic, for instance. So we're laying them with a 38-meter float times 8 meters with the long sides towards the wave front. And that way we can lift up to 600 tons. And then, just to continue slightly on that one, you can use Archimedes' laws in two ways. Either you are resonant, which is jumping up and down in the waves, like a kid on a trampoline. You're trying to make higher oscillations than the wave itself. Or you can go non-resonant. That means you're going slowly upwards like a weightlifter, lifting perhaps just half of the wave height, but with tremendous force. We're in the latter category, and that has many advantages. We can come back to that. But basically, that are the principles in use today.
Okay. So tell me a little more about your solution. How are you actually generating power from the wave motion?
Yes, we have stolen or borrowed the hydropower plant, which is up in the mountains. There you have a dam. You have a tube going down, perhaps 500 meters, causing 50 bars of pressure. And that pressure is then converted into water hitting a hydropower plant or a turbine with high speed, normally a Pelton turbine. And that spins around quickly with high energy. And on the same axis is a generator, which creates energy then and goes out to the grid. So we have the same system, just upside down. So what we do is that when we are in the lowest in the wave, we lock the system. It cannot move upwards. And we have a hydraulic cylinder going below the float with a piston rod going down to the seafloor, also with a wire on the end there. And when we have the pressure we need, this water-filled cylinder presses the same 50 bars of pressure upwards, the same Pelton turbine, the same generator, and creates energy, which goes then via a seafloor cable into land. So it's just a hydropower plant coupled to a hydraulic cylinder, coupled to a float. So basically 3 parts. Very simple, few parts, light parts, which is then different from anyone else. That's why we have this tremendous power. And how much power does it give? As I said, the lifting force is 600 tons in waves of 45 meters. Normally, of course, less because waves are anything from 1 to 4 meters normally, depending on summer, winter, and location. But in higher wave, you are hitting that turbine with about 2,000 liters of water per second, 2 tons of water, with up to 300 kilometers per hour. Imagine taking your neighbor's car, crashing it into a brick wall at 300 kilometers per hour every second. That is 6 megawatt of power lifting force in those seconds. The average output or what we can do at most then is 700 kilowatts in higher waves. If you have continuous, let's say 4-meter waves outside your original home country town, island.
Yeah.
But of course, then outside Spain, for instance, you would average on the coast there, perhaps 250 to 300 kilowatts per year. More in winter, less in summer.
Okay. So talk to me a little bit about geographical differences. Where are good sites for wave farms and where are less good sites? And why?
Yes, we come back slightly to how the winds are created. They're created by rotation of the Earth.
Mm-hmm.
And then the heating of the air masses, different over land and sea, and then low and high pressures. So waves are created over time and distance, going then from the west towards the east. That's why I spend longer time flying an aircraft from Europe to New York than the other way around, because you have tailwinds coming back. And those tailwinds are creating waves over distance then. So on the west coast of the continents of Europe, Africa, and the American continent, plus Australia, New Zealand, Japan, Indonesia, for instance, you have strong westerly winds and waves coming in. That's where you have the bang for the buck. And then there's a belt around the equator from about 20 north to 20 south, where there's less wave height. The waves are though very long and nice like swells, so it's possible to use them just with the larger floats in our case. But most wave power systems do not work well in those areas because they are resonant. They go up and down like the trampoline system. And then you have too long time distance between the waves. And then you have more energy than from 20 north to about 60 north. And the same on the southern hemisphere. So in practical use, then from Trondheim in Norway, all the way down to Mauritania, excellent waves. Then you have Namibia and South Africa, excellent waves. And then you have Alaska, Canada, US, basically, less of Mexico. And then it's Peru and Chile. And then, as I mentioned, the Asian countries, Japan, New Zealand, Australia, and all those are excellent. I think 13 of the 20 most polluting countries in the world have excellent wave conditions. So we can make a huge difference that way.
And when you say polluting, are you talking about carbon pollution or some other form of pollution?
I was thinking carbon pollution, yes.
Okay.
CO2, yeah.
Yeah, just to clarify. Cool, great. There's also the challenge with wave power that there's not a lot of people on the water trying to use the electricity that it would be generating. So how are you moving the electricity from the wave farms to where the demand for electricity is?
Yes, it's basically the same as wind power. You have floating offshore wind and you have fixed-based offshore wind. So let's say you have 20 or 50 units out there as an array, it's called. In our case, they're spaced 200 meters apart. Wind power turbines need to have 1 kilometer apart. So we get more energy per sea area than wind power, by the way. But then you have old cables coming down to a subsea collection hub. And these cables are dynamic. They can move with the float up and down. Exactly the same thing as with offshore floating wind. And then you have a fixed stationary cable on the seafloor going into land. But there's one big difference. Wind power offshore will normally be located up to 50 kilometers offshore due to they go high up in the air, up to 250 meters, and they are making noise and disturbing, and no one wants to have them outside their own, let's say, window. It's fine with someone else's window, but not their own window. So, yeah, that's how it is. But wave power, the waves have full force coming into the coastline until they start hitting the seafloor. That is at a depth of about 30 meters. So we can be located from 30 meters to 200 meters depth. Normally from 30 to 120 is more practical. And that would normally be from anything from 500 meters to 5 kilometers out. So we have much shorter cable, much shorter OPEX, the cost of maintaining the systems or operating them. And then in addition, they are hardly visible because they are much lower, of course, than wind power, and then don't make any noise of significance. So you're saving costs in that way. And of course, the cable is much shorter. They can, though, be co-located with offshore wind power. So those listeners which are in that segment, happy to contact me and talk about co-location of the wind power plants, where then lowering the, let's say, crashing impact onto the turrets because of, we extract energy from the waves, they get lower. And we can be in between the wind power turrets and more than double output from the same sea area. So if you have a certain that cost for operational rent, of course you can, let's say, divide or split that cost on more units. So it's sensible to co-locate them. Also because there is a lack, of course, of sea area coming up in the future. So why not co-locate?
Sure. What about co-locating with solar? Because I know there's a rise now in floating solar as well.
Definitely needed. We can co-locate, but as you might have seen on some of your information, we have, since we now already have the flow, we have the cable, we have the mooring lines, we have the communication system like also solar power needs to have. So we said, why not use our flow as the base for solar panels? So now we have actually applied for grants from the European Union, from EIC now, for designing and installing between 400 meters to 700 square meters of solar panels on top.
Hmm.
That's about, plus minus 100 kilowatt peak from a solar. It makes sense because we don't have any cost for the flow, the anchoring, and the systems on board, which they have, and the cable. So it just will combine us to a hybrid solution. Also, in the summer months, there's less wind power and less wave power, but there's some power. So by combining that, you always provide lots of power, either by wave power or by sun power. Of course, majority from the wave power, because waves are much more dense than solar and wind. But it's a nice addition and it costs very little. So we are also floating solar.
Nice. Nice. Okay. One of the criticisms generally of renewables is the fact that they're intermittent. The sun obviously is only up, depending on where you are, 8 to 10 to 12 hours per day, sometimes a little more in summer, and depending on how north or south you are. And the wind, obviously, as well, isn't always blowing. There are always waves, not always the same height, not always the same frequency, but they are going up and down and up and down. So the electricity you're creating is obviously coming in bursts of those 700 kilowatts or whatever it is as well. How is that addressed?
There are two aspects to this. Let me first of all into this intermittency of wind power and sun power. Of course, sun power is gone for 12 hours or more per day. And wind power is basically down to 10% for 10 days a month. If you combine these two sources, that's 40% of the hours of the month. There's little wind and no sun. So what do? We, of course, pay huge prices for the electricity bill those days when there's little wind and no sun. It's been fluctuating, widely this winter, for instance. And that's due to the lack of those clean energy sources. And so we burn fossils, coal, gas, and oil, those hours, the main extent. Of course, there's a base load of hydropower and those which can be adjusted somewhat up and down, but mainly we burn fossils. And then, of course, you can have storage by batteries and some other sources as well. And the battery storage as grid scale is basically impossible. The number of batteries, the amount of cobalt and lithium needed is impossible to extract at grid scale. For households, yes, and electric cars, yes. But it's not possible, the amount of batteries needed. But luckily, you know what I'm going to say? There's wave power. So in those hours when there is no wind and sun, there's normally wave power. And how come? Well, the wind over time and distance, as mentioned, creates waves. But when the wind goes down, we all know that the waves remains for days, hours and days. So in those hours and days when they're burning vast amount of fossils, when the utility companies are scratching their head and looking into, how can we solve this? Then you have wave power, lots of wave power, clean energy. So in my mind, you can choose between going then wind power, solar power, and fossils storage, or you can go wind power, solar power, wave power, and much less fossils and storage. It's actually a no-brainer. And so far, not so many know about this, but it's coming, I can assure you, because there's a huge problem and there's a solution. It will happen, no doubt, big time.
Okay.
And then regarding, you had the second question was about the intermittency from every unit. Yes, we provide 700 kilowatts and then nothing, 7 kilowatts hour. And that has no influence on larger grid. It doesn't matter because there's just like switching the factory, lights on and off in a factory or turning on a machine. On smaller grids, we can alleviate that by having supercapacitors on board, which evens out the power. But of course, if you have 5 units or more, they're hitting the waves at different times, then it by itself is evens out. The 1 unit is more of a problem. If you have 5, 10 or 20, 50, it doesn't matter, it's just stable.
Okay, perfect. What about the cost? Because the cost, if it's too expensive, it doesn't matter how efficient it is in terms of its generation. it will only succeed if it can be competitive with, unfortunately, fossil fuels.
Definitely. Many talk about, helping the environment
Hmm.
and want to do it, but there's also always the cost issue. So it's difficult today to convince the shareholders to spend money on something which they lose money on. Basically, it's difficult. Wind power and sun power started at about 70 cents kilowatt hour. Now they're down to, onshore wind is down to, 5 cents. So in that range, offshore wind power, it depends on the area size, anything from 5 cents to 15 cents per kilowatt hour. And then they are going profitable. But they had subsidies for 20 or 30 years. And that subsidies coming from the governments mainly made them have a learning curve going down there. And once they can come down to, about 10 cents or 15 cents, we saw an explosion in the deployments.
Yeah.
Because they were, becoming basically able to make money also besides the subsidies. Subsidies also, of course, going down over time. And the same thing happened with solar panels. Once the costs were coming down, bang, went up. And the same thing will happen with tidal power and wave power, no doubt. The subsidies right now for tidal energy is around 25 cents in Canada and in UK and in Taiwan. For wave power, it's mainly right now only in Taiwan. And the European Commission has stated that they will see or make subsidies, etc., available or incentive is a nicer word, to make this happen, because they want to see 500 megawatt deployed of ocean energy in Europe by 2030. And they want to see 40 gigawatt, it's 40,000 megawatt, deployed by 2050. And since the cost for wave power, in general, is from 30 to 50 cents per kilowatt hour now in the beginning, they will need to make similar subsidies as they made for wind and solar, but just 50% of level because we are cheaper than they had. So let's say it this way. We are starting at the cost on our unit, which is below 25 cents. So we're starting at the cost which is below what wind power and sun power had. Okay, so we add the same learning curve. Steep in the beginning, then more shallow. But it indicates quite clearly that we will be going below, mind my words now, below offshore wind in some years in cost per megawatt hour. Add to that we are more stable. It's a better energy source. Then the potential is huge. Of course, business-wise and also for the climate change, because we can mitigate the use of fossils and storage. So we're talking big numbers here, very big numbers.
What kind of numbers?
Well, the estimation is that by IPCC, for instance, that wave power can deliver the same amount of energy worldwide as all of today's electricity consumption. All. That's 29,000 terawatt hours per year. So that is quite, there's basically no limit to any company which does this properly. Money-wise, by 2050, if we take just 10% of the European market, that should equal about 12 billion in sales just in Europe. The global market is 6 times larger. So we are talking closely, in the possible range of 100 billion in theory, at least. That should be enough for most, let's say, investors and other ones. The potential is huge. And I believe it is potentially larger than offshore wind, because offshore wind has twice the weight per kilowatt hour than we have, twice the number of parts. They need twice the area. And let's say we are 3 times more stable. But then again, if you combine then the wind power and the wave power, the base load is up to 5 times higher than just having wind power by itself. So we can help the wind power guys also make more money by owning both wave power and wind power at the same time, because they can deliver clean energy which is what the customers want, and having to spend less time on storage, for instance, which does nothing.
And to your earlier point, for wind farms who might be paying rent on the ocean floor, you can help them get better value for the rent they're paying by increasing the amount that they generate. Plus, also the infrastructure costs are reduced for you if you're co-locating there because they already have the distribution cables in place, right?
Correctly. I think most people would like to get double the bang for the same money. Uh, and that's what they're getting. It's again a no-brainer. You get double the power from the same sea area, of course, is very useful. And then, of course, you have maintenance people going forth and back with the large boats and stuff. They can, of course, maintain and look after both wind power and wave power at the same time. And any, let's say, regional governmental agencies will love to get more power from the same area because, also you have fishermen, so you have shipping lines. There's all will be more and more competition also for the offshore sea area. So anyone will be happy to see more power coming from the same area. It's very logical. Yes.
Okay. There's a criticism as well of offshore wind farms of the environmental impact on sea life or bird life, or, have you studied that for the wave arrays? Is there an environmental impact that they have?
Yes, it's a good question. Let me comment something on wind power, which I read some time ago, which I think is important for which most people don't know about. The onshore wind power turrets in Germany, every unit, the size is perhaps in the range, so 1 to 2 megawatt mostly. They're each killing 40 kilo of insects every year. 40 kilos.
Wow.
And 40 kilos of insects, that's probably the volume of your house or more per in a wind power unit. And nowadays, the number of, if you drive the car in the afternoon, you will see that the amount of hits by insects is measured to be 10% what it was, 20 years ago.
Mm.
I'm not saying that wind power solely is responsible for that. There are many factors, but it's important. The mosquito bites I've had this summer or last summer is nothing compared to what I had when I was a kid. And without insects, we have a problem. So that's one, let's say, challenge for wind power owners to look into. Not so well known, but they have seen so far zero negative effects by wave power. Nothing on the seafloor, no fish, no organisms are being trapped by this. So far, the results by quite a few investigations have been very positive. Same also goes for tidal, by the way. They have a prop going around underwater, and there's been extremely little impact. The fish swim around, even if that goes quite slowly, by the way. But so tidal and wave power so far has zero negative impact on nature.
Sure. And where are you guys with your wave generators now? What kind of stage of development are you at?
We're at so-called TRL6. That means we have tested it in, first of course, deep simulations by third parties. Then be that a 1 to 5 or 1 to 8 scale, depending on how you measure it, prototype out to sea for 5 months in wave tanks, two times in England and 1 time in France. And then we have been validating those numbers by our simulations model. And the essential thing is here that our simulations matches the output from what we get out to sea perfectly. It's 100%. The curves are the same. But we then extrapolate those numbers to the full scale unit. We get actually close to 1 megawatt of output in waves of 45 meters, which is unique in this sector. I'm saying that 700 be more conservative. We might change the number, which is said officially it's 500 kilowatt now because we have shown these numbers. So now we're going in from this prototype level to the full scale design. We got European funding for that, about 2 million euros, and also some from the Swedish authorities. And that is for the design and the production, deployment, and testing of the full scale unit, 38 meter units. It goes in a test site, most likely close to you outside Spain, just north of Bilbao. There is a test site called BIMEP, which we will be deploying the float in less than 2 years. And then a half year later comes the machinery, the power takeoff into the middle there. That is our plan so far. Of course, this doesn't come at peanuts money because the first unit is always very expensive. So we would like partnerships with larger oil companies, utility companies, industrial companies, shipyards, perhaps a constellation where they all pinch in a little bit and we do it together. Or if one major partner want to see their own name on the side, on the floor, perhaps 35 meters long, says Shell Renewables on every front page of the larger magazines coming up, quite often. And then later on, having people coming on board, the CEO, VIPs, media, and perhaps royals coming on board the float in 2 and 3 years. I think that's very important for them because they're doing something sensible. They're showing that they can do something more than just look on and sit on the fence. And I think also for internal marketing, if you are Shell, BP, Equinor, or other oil companies struggling with attracting, young people coming into the sector, qualified people, then of course you can show that, well, we are doing something. We are doing something sensible, just more than just buying another, wind power turret here and there. You're doing something new, taking a little risk, small money for them anyway, and then show that you do something sensible, bi-monthly newsletters, having your employees coming on board. I think we can do something for them this way. So both internal and external marketing is what we can offer them to come along on this exciting journey.
And what's the revenue model from this?
There are 3 revenue models. One is own production and turnkey, delivered to the utility companies or islands. There are 2,000 islands globally that mostly run on diesel and PVs. And they also are, of course, interested in having clean energy because they are seeing perhaps more than others the hurricanes and the rising sea levels coming in. And so that's turnkey. And it's also BOO, build, own, operate. Because later on, we will see that we're starting at then around 20 cents per kilowatt hour. But after 200 units, we're coming down to half of that because of the learning curve. And that's 10 times quicker than wind power and sun power did. They needed more than 13 times more deployed capacity before they came to the same cost level. So in that case, you could have 100% profit per kilowatt hour in theory, at least, for that. So it's important also to own ourselves. Might not come first. And then you have the partnership, working with partners also for production, and they can have their own build, own, operate. And then you have licensing, because we can build perhaps 50, 100, 200 per year in our production line coming up. But if we have 10 or 20 licensees around the world doing the same production, perhaps costing just 100K per unit in license fee, then those companies can help us deploy thousands of units over the coming decades. That's how we make a big difference for the climate change. That's my goal. I do this 60%, I say, for the climate change to mitigate. I'm not a young man anymore, so it's not the other motivation. So 20% for the money, fine, good for my children, and 20% because I like doing a project. I think it's just fun, entrepreneur.
Nice.
Okay.
Jan, we're coming towards the end of the podcast now. Is there any question that I have not asked that you wish I had, or any aspect of this we haven't touched on that you think it's important for people to be aware of?
I think we touched upon the main areas. One more philosophical thing is that, yes, wind power and sun power is large right now because they came first, basically by accident. I had this in my drawer, since I was 25, and it could have been same as wind power today, possibly. So wind power came first before us. It doesn't necessarily mean that it's better. It was just first. So time will show. I think we have a good chance of being better in many ways. The sense is, of course, working together, the energy mix.
Mm.
And then, of course, since we use less material per unit, our climate impact, the amount of emissions, the life cycle emissions is lower. So for, every unit per year will produce a savings on the climate of about 500 tons of CO2 per unit per year. And the emissions, the life cycle emissions, is a 7% of the European Union's average emission per megawatt hour, including all the wind power and solar power or renewables and hydropower plants. So because of the lightweight and so by having a very short carbon payback time, we can make a huge difference for the climate. Other systems require more years to go break even if they even do that. So I think that's also important for the ones that think more than just on the business side. We can do something important also for the climate in having less emissions per unit per lifetime. And also, if I might add, the lifetime we're aiming for is 40 plus years.
Wow. Impressive. Cool. Jan, that's been fascinating. If people would like to know more about yourself or any of the things we talked about today, where would you have me direct them?
Could be, of course, to our homepage. Just Google NoviOcean in one word, and you will find the homepage. We have everything on it, the simulations, the data, the output, the presentation, even the business plan is presently on the web page. And also, if someone is more serious in perhaps investigating how we can help them on the business side, most welcome to contact me personally on LinkedIn. And there's also many posts that, of course, they can read about. And they can even see this interview coming up in a while on LinkedIn. So welcome to have a chat, and we have time for that. And I do enjoy talking business with anyone.
Perfect. Great. I'll put those links in the show notes as well, Jan, so that people can find them there. Super. Jan, that's been fascinating. Thanks a million for coming on the podcast today.
Thank you, Tom, for having me. A pleasure.